Good morning. Today we are going to uh, recall what we did with an infinite sheet of charge using Gauss's law. So um, we looked at this problem before. Suppose you have an infinite sheet of charge, right? And this is going all the way to infinity. We discussed this in greater detail earlier. So you can go back to that if you don't understand this completely. And to find the field, we saw that the electric field on the top is pointing up and electric field at the bottom is pointing down. And by the symmetry, we chose a Gaussian pillbox that looked something like this, right? And extending below, um, so something like that. That was the Gaussian pillbox that we had chosen. And we saw that for the sides, the area vector is perpendicular this way. So there is no contribution from these sides that don't contribute to the flux. And also, even if you didn't know which way the electric field is pointing, you could still make this side, the contribution of the sides, go to zero, because you could choose an arbitrarily thin box. So you can send the thickness of this box T to almost zero. So if you send the thickness of this Gaussian pillbox, to zero, then the sides are so tiny that they almost contribute nothing in that limit, right? So even if you didn't know the direction of the electric field, you could simply use that technique to see that the sides don't contribute anything to the flux. For the top one, the flux is, the area vector is pointing up and the electric field is E. So for the top face, the flux is EA. And for the bottom face, the electric field is pointing down, but the area vector is also pointing down. So 2 times 2 negatives basically give you a positive EA for the bottom, right? So then we get the total flux, which is given to us by the surface integral of E dot dA, and the surface we chose is the pillbox. The sides don't contribute anything. The top contributes EA, bottom contributes EA, so the total flux is 2 EA. But from Gauss's law, this is equal to the total charge enclosed by epsilon naught, and the total charge enclosed in this would be, you are enclosing an area A of the surface. And if the surface had a charge density of sigma, then the total charge would be sigma times A. Sigma is charge per unit area, so you multiply with area to get the total charge by epsilon naught, or A's cancel out, and E comes out to be sigma by 2 epsilon naught. And if we want to write it in the vectorial form, it is this, where N is pointing up on the top of the surface and down at the bottom of the surface. So with this, now let's look at something that I mentioned in the last lecture about the boundary conditions. So let's take this sheet of charge here and write down the electric field. Here it is sigma by 2 epsilon naught, and it is this way, sigma by 2 epsilon naught. So this is above and this is below. So if I were to write, if I'm going across this from below to above, I have to go through a charge distribution. So the electric field across this path is not continuous. What we mean by that is, if I take the field above and subtract the field below, if you look at the from the vectors, right, you basically get sigma by 2 epsilon naught minus, right, minus of minus sigma by 2 epsilon naught, because the electric field below is pointing other way, so you have an extra negative here. So minus times minus gives you plus, so you have 2 times sigma by 2 epsilon naught, or you have sigma by epsilon naught. That means when there is charge at the boundary, the electric field across the boundary, the electric field is going to change differently. It's not continuous. We have seen this even for a spherical shell of charge in the last lecture. So if I have a spherical shell of charge, I'm drawing the cross section of a spherical shell of charge. We saw that at any point inside, by symmetry arguments, if I take a cone of charge here, that should point the electric field down, but on the other side you should have another cone that has the electric field pointing up, so these cancel out, so electric field is zero inside a spherical shell. But outside, if you assume that you are very far away from the spherical shell, then it may look like a point charge to you, and you see electric field that is not zero. So as you go from inside the spherical shell to outside, there is a discontinuity in the electric field because there is a charged boundary in between. Same here, as we go from below, where we have negative sigma by 2 epsilon naught, the electric field pointing downwards, to the top, you see a change. The electric field on the top is now pointing up, so there is a discontinuity of sigma by epsilon naught. So this is the perpendicular component, as you can see, of the electric field, right? So the perpendicular component. But let's talk about a little bit about the parallel component. We'll show why the parallel component doesn't change, or it is zero in this case. But in general, if you have some curved surface instead of flat, we can see why it should be zero. So if you have a curved surface, you can take a small region of this and zoom in, right? And that small region looks like this. That is, I'm zooming in here, so it's somewhat more or less flat, and then we can see that the parallel component, for the parallel component, we can draw a loop, right? We can draw a loop like this, where we're going this way, here, and this way, and across this loop we can calculate E dot dl across this loop. So we can make this loop, arbitrarily thin. So we can send the thickness to zero, right? So the sides don't contribute, because we can make it arbitrarily small. So I can make it almost like just like this, with a very tiny side. So I can make it arbitrarily small, so I can ignore the contributions from the side. But then you can see here that I will have, in this direction, I have E above times L, and below I have E below times L. But we know that the path integral of E dot dl is zero from Stokes' theorem, right? We know that the curl of E is zero because we expressed E as a gradient, right? Gradient of phi. So curl of E is zero, or from Stokes' theorem, this E dot dl, the path integral is zero. So E above L minus E below L, where L is the length of the loop, is zero. You can take the length to be common. So E above, this is the parallel component of E that we're talking about. E above is equal to E below. So there is no discontinuity for the parallel component, but there is a discontinuity for the perpendicular component. So for the perpendicular component, E above minus E below is equal to sigma by epsilon naught. Now this means we can write the potential, right? And we can write these boundary conditions in terms of electric potential. So we can write this electric field above as a gradient of phi, right? Above, negative gradient, times negative of negative gradient phi below, is equal to sigma by epsilon naught. If you take these negative signs, you can put them on the other side, and you would see that grad phi above minus grad phi below should be negative sigma by epsilon naught. So this would be the boundary condition for the in terms of the potential. The potential itself will not have any discontinuity. The reason is, if I have a sheet of charge, right, I go from below to above, right? So imagine there's a point B below and point A above, and I'm going from above to below, right? And I want to find the potential. So the potential is simply negative E dot dl going from A to B, right? So now I can make this dl, I can make this dl as small as I want. I can make this dl almost zero, right? So if I make this E dot dl zero, I can get this total V, which would be essentially V at B, V at A minus V at B. So if I shrink dl to zero, that is if I just go from right above the surface to right below the surface, this length is arbitrarily small, so this integral is zero. So the left hand side, which is the difference between the potential, this is the potential difference, delta V, right? So you need to bear that in mind. We're going from point A to point B, right? So there is a difference in potential. So there is an electric field because of that difference in the potential, right? So this, while going from A to B, the resultant is the difference between the potential of A and B. So that is zero. So VA is equal to VB. So the potential above is equal to potential below, but the gradient of the potential changes. The gradient, the way it is increasing, the rate of increase changes because um, there is a charged surface in the boundary while going from above to below. So the result of this charge appears in the gradient of the potential and not in the potential itself. Okay, so these are the boundary conditions. Now let's talk about capacitors. This is the last topic in chapter 2. So if I have two metal plates, right, and I want to take some electrons off the first plate, so this is plate 1, let's call this plate 2. So I'm taking some electrons off of plate 1. So plate 1 is positively charged because I'm ripping electrons off. And through some wire, I want to take them and put it on the other plate. So I want to put this electrons on the other plate. So if the charge here on the positive plate, let's say, is Q, that means you have taken electrons that have a charge of negative Q. So you have a positive Q on the plate 1, and you have taken these negative Q charges and somehow put them on plate 2, right? Then because this has positive charge and this has negative charge, there is a potential difference between these two plates. Now we can calculate that easily because we know that we know that if this is a flat sheet of charge, then we know the electric field here is sigma by 2 epsilon naught, and this is positive, so it's going out. For this negative plate, it is going in because it is negative charge, sigma by 2 epsilon naught. We write these directions based on a hypothetical positive charge. So we write this direction by assuming that if I were to bring in a positive charge here, which way would it go? So if I bring in a positive charge here, a positive test charge, it would be repelled away. So that is the direction of the electric field. Whereas for the other plate, if I were to bring in the same positive test charge, it would get attracted, right? And on this side, if I were to bring this thing here, it would point this way, and here it would point this way, right? So if these plates are very close, then you can assume that the fields outside the plates almost cancel out each other. But in between the plates, you can see that you have 2 times sigma by 2 epsilon naught. So the total electric field within these plates, between these plates, would be sigma by epsilon naught, where sigma is the charge density. So what this means is that if I increase the charge, right, then the potential is simply E times the distance between the plates. If the distance between the plates is d, then that is going to be sigma by epsilon naught d. That is the potential. So we see that there is a direct relation between potential and charge. So if I increase the charge, that is, if I were to take off more electrons from plate 1, if I were to take more electrons off plate 1 and put them on plate 2, then I'm increasing this charge density. I'm pulling more electrons off. So then the voltage difference should increase. So there is this constant of proportionality between charge and voltage, and in general we call that as capacitance. So this capacitance C is equal to Q divided by V, the constant of proportionality between charge and voltage. So in this case, I can write V is equal to the charge is simply charge density is Q by A, where A is the area of the plate, times D. So if I were to do Q by V, then that would be the capacitance, that is epsilon naught A by D. So this is what you know as a traditional parallel plate capacitor. But the idea of capacitance is like what I said, that if you were to pull more electrons off of plate 1 and put them on plate 2, the voltage difference between them would increase. Why is this the case? Let's do a simple analysis, right? Let's say to begin with, I have let's say I have taken some charge little q of the positive plate, some q electrons of the positive plate, and I put them on the negative side, right? So here I have negative q. That's the total charge here. Assume that I have done this. Now I want to take some more charge from plate 1. I want to take some more charge dq from plate 1 and transfer that to plate 2. So I want to take some more electrons, which would change the charge of the positive plate to q plus dq, right? And put them on the negative plate, so I can change that to minus of q plus dq, equal and opposite. But to do that, there is a problem here because these are positive charges here. Positive charges are naturally attracted. Their electric field is pointing this way. They are attracted towards the negative charge. But you want to take these positive charges in the opposite direction. You want to pull them away from plate 1 and then go around and put them back on plate 2. So you are going in the opposite direction to what this positive charge wants to do. If you let this positive charge just be, it would go to the negative plate because of the natural attraction, but you are having to oppose that attraction and go around it. So you have to apply some, you have to do some work to move this charge dq from plate 1 to plate 2. And we know how to calculate that work. We have seen that work we can calculate as potential times dq, right? But we know that potential and the capacitance are related, right? So we saw that q is equal to cv. So v is just simply q by c. So the potential here in this plate is q by v, or q by c, sorry, because the charge is little q. So I have to do a little work dw, which is equal to the potential against which I am working, right, dq. There is a natural tendency for the positive charge to go this way, but I have to do work to go the other way to transfer this charge dq from plate 1 to plate 2. So if I calculate, going from 0 to q, what is the total work done? Then I can see that it is 1 over c q dq, 0 to q, which is 1 over c q squared by 2. Right? So I'm doing work of 1 over 2c by q squared, right? So I am increasing the potential here because I am putting that energy into the system by doing work to pull this charge dq off plate 1 and transfer it to plate 2. I'm doing this work, and that work is stored as the potential energy. So the potential difference increases proportional to the charge, because I'm doing work to pull that charge off and transport it to the next plate. Because we know that Q is equal to CV, we can rewrite this equation as 1 by 2C. Instead of Q square, I can write CV square. So that gives you 1 by 2C, C square V square, or half CV square. So by looking at this, you may remember the potential energy stored in a spring mass system. If I have a spring of spring constant K and a mass M, and the elongation is say x, then the potential energy we know is half kx squared, right? Because we are applying a force of negative kx, right? So this k is sort of the a constant between f and x. So in a very similar way, here the energy in the capacitor system looks like half CV squared. And here the variables are, instead of x and f, here what the variables are, if I have to move a charge dq from plate 1 to plate 2, then I do work, and because of that work, the potential difference increases. So potential difference is proportional to the charge, and the constant of that proportionality here, like the spring constant, is what we call as capacitance. Now here there is a tricky thing. The tricky thing is that when you're considering these plates, plate 1 and plate 2, we're assuming that these plates are metallic. And this assumption is very, very important to reconsider, because all materials are not metals. And in metals, there is a free electron C, like I have mentioned when we're talking about conductors. So even if you rip charge off, a little bit charge off, and put charge on, there is enough place, enough energy state for these electrons to go into. But very often, especially in fighting the climate change, there are these new batteries and capacitors that are coming out which have better power and better energy. These capacitors do not use metallic plates. They use semi-conducting plates, or sometimes semi-metallic plates. And when they do that, there is an issue, because when you are dealing with semiconductors or semi-metals, it is not so easy to take charge dq from here, because charges are pretty much very immobile in the semiconducting and semi-metallic plates, and put them here. It is not as straightforward as you do in metals. In fact, when you take quantum mechanics, you will learn that the electrons in these systems are distributed in specific energy states. And when you are bringing in new charge, you cannot just add charge how much ever charge you want, but it depends upon what is the next energy state available. So the energy doesn't necessarily increase linearly, but it goes in abrupt jumps. So that has to be considered, and there, when you consider that, there is a quantum effect called quantum capacitance. And this quantum capacitance, the reason I'm mentioning this is that this quantum capacitance plays a big spoiler, because the quantum capacitance is often very small. And if you have two capacitors in series, so if I have two capacitors C1 and C2 in series, the effective capacitance is 1 over C1 plus 1 over C2. And because the quantum capacitance is so tiny and it falls in series, it dominates most of the times. And this is the reason why even in your computer chips, if you are a little tech savvy, you do know that there are these silicon channels going from one end to another end. So this is a silicon channel in the transistor in your chips in the computer, and then this width, when you are depending upon this width, the quantum capacitance of this channel plays an important role. And as you're shrinking down to 7 nanometers and below, there is a technology that is coming up. These quantum capacitance effects, they are very evident, and those are not very easy to address. And that's going to be one of the challenges going down, in addition to lithography and other things. So I just wanted to mention how that is relevant for ICs, because there you don't really have metallic. Here you have a silicon channel, which is semiconducting. So the capacitance would be very different from capacitance for plates. Whatever analysis we have done, bear in mind that we have done this analysis considering the plates to be metals. And when the plates are not metals, then the quantum effects have to be considered, and it is not as straightforward as this. So this ends our discussion entirely on chapter 2. So far we have defined what E field is. We have also defined what potential is, and we have seen Gauss's law, and we have solved problems using Gauss's law, and then we looked at the boundary conditions. And while talking about the potential, we also looked at the multipole expansion. And most important equation that we have seen is the Poisson's equation and the Laplace equation. We got this from simply by putting Gauss's law, del dot E is equal to rho by epsilon naught, but E is grad phi. So then you have negative of divergence of grad phi is equal to rho by epsilon naught, or the Laplacian here of phi is equal to, sorry, this is a scalar Laplacian, is equal to negative rho by epsilon naught, right? And if rho is equal to 0, then we saw that del square phi is equal to 0, and we call this the Poisson's equation, and this as the Laplace's equation. So in the next chapter, we are going to discuss the Poisson's equation and the Laplace equations, and see look at different ways to solve problems where electric field and the potential are not directly evident from the symmetry. And that's what we are going to do in chapter 3. Thank you.